to all of you. So first and foremost, welcome to all of you and very good afternoon. Actually, this subject, this advanced propulsion systems for future space exploration, this is tailored to you with cutting-edge knowledge in one of the most crucial areas of modern space exploration. Basically, as you know, that this understanding about our propulsion technologies, it is very important as we continue to push the boundaries of what is possible in space. From satellites to deep space mission to Mars and beyond, the propulsion system is playing a very, very key role in determining the success as well as the sustainability of the endeavors. And though it's on advanced propulsion system, what I thought is, we will just cover traditional chemical propulsion system and to the next generation systems, like we talk about these ion thrusters, we also will talk about this nuclear propulsion and so on. So first, let us get started. Hope all the slides are also visible to you. As you know, in ISRO, basically there are various generations of launch vehicles which have already been designed as well as developed, realized, tested, and then flown. So what is shown in this figure is a series of such launch vehicles, starting from the sounding rockets at the extreme left. These are all very small rockets, which get into the atmosphere and with a small payload. And the main purpose of these payloads are just carrying out some measurements of our atmosphere. So these, even today also, the Rohini is a kind of a sounding rockets. It's called RH, RH300, RH500, 560, like that. Different classes are there. Even today also, these are also being launched, mainly for carrying out such purposes of carrying out the measurement of the atmosphere. And moving further towards the right, you are seeing two small launch vehicles, which are called the Satellite Launch Vehicle 3, SLV, and similarly the ASLV, Augmented Satellite Launch Vehicle. These two were the initial generation of the launch vehicles during the 1970s and the 80s. And the project director of the Satellite Launch Vehicle was none other than our former and late President Dr. APJ Abdul Kalam. And there were a number of missions of both SLVs and ASLVs. Of course, initial mission was a failure, but then later missions of SLVs and ASLVs were grand successful. But then when we graduated the rocket technology, we moved on to the next generation launcher called the PSLV. This has come from the 1990s. And even today, the PSLV, the Polar Satellite Launch Vehicle, is one of the very workhorse launcher of ISRO. And recently, on 30th of December last year, we had a grand successful mission, which has taken SpaceX. A few days back, we had the space docking experiment. The two satellites, SpaceX A and SpaceX B, was launched by the PSLV, and then we had a mating, or we had a docking of these two satellites, which got demonstrated a few days back in the orbit. So then India became the fourth country after the US, China, and Russia to have this technology of docking in space. And then moving further right, we have the GSLV, Geosynchronous Launch Vehicle. This also has come into operation from 2000s onwards. This is a launcher which is actually designed for launching geosynchronous satellite into a geostationary orbit. And moving further right, we have the LVM-3. That is called the Launch Vehicle Mark III, which is otherwise a nickname called the Fat Boy. Because out of the group, this is fat in size, so it's a name like that. But otherwise, it is a Launch Vehicle Mark III, which also is intended to carry geostationary orbits, geostationary satellites into geostationary orbits. And to just note that, this particular launcher, already 7 missions we had, and all the missions were a grand successful one. Even the latest, the Chandrayaan-3 mission was executed grand successfully by this particular launcher. And in fact, you also please note that this launcher is designed for carrying humans into the orbit. That is, as part of human space exploration, this launcher is also getting human rated. And that mission also we are going to have in the first half of this year with the unmanned missions. And the far extreme right is a small launch vehicle. Again, you are seeing, this is named as SSLV, which is actually the small satellite launch vehicle. This is also looking into the market of carrying small kinds of payloads of the order of 500 kg into a 500 kilometer orbit. This launcher has been optimally designed with a low cost and anytime launch, so that once the demand is there, within a week, you can realize and then integrate and test and then launch. So that is how the small satellite launch vehicle. So these 4 launch vehicles, the PSLV, GSLV, launch vehicle Mark III, as well as the SSLV are today currently in operation. Why I have put this slide is only to tell you that these gigantic vehicles, which are 40 meters or above tall, and which are weighing from 200 tons to almost 600 tons, they are all using propulsion systems of different kinds, like solid propulsion, liquid propulsion, and that even we call it as storable as well as cryogenics. Maybe we will go into the details of that later. Just to put you in perspective, all these things are powered with the huge propulsion systems. Now let us see the satellite propulsion. Similar to the launch vehicle, we have various satellites, starting from Aryabhata. In the year 1975, we have launched, and then various kinds of the Stretch Rohini satellite series, which is otherwise called STRAS. And today we are talking about very heavy launches such as GSAT, geosynchronous, the satellite 11 and Chandrayaan 3. These satellites also carry the most important, the propulsion system, because once you are reaching the orbit, you need to maintain the orbit, that is the 3-axis control in pitch, yaw, and roll, that is maintained by the propulsion systems. And we also use bipropellant or even monopropellant liquid propulsion thrusters to do that. So, and then we are also seeing the bottom, whatever that is shown is the application, what for the satellites are put in orbit, like Earth observation, SATCOM application, that is satellite communication, navigation application, it's called NAVIC, then disaster warning like cyclones and tsunami, kind of a disasters, if it can be warned. And then there are various strategic applications to, to monitor the borders and things like that. So various applications, various kinds of satellites are provided, and various kinds of propulsion systems are also there to ensure that the satellites remain in the orbit with its 3-axis stabilized. Now let us look at what are the classification of propulsion. As you are all students and there are space enthusiasts, some of you might be knowing that there are various kinds of propulsion devices. Basically, propulsion devices are the one which keeps you moving forward. So we can have like a stored gas propulsion, the extreme left top, it is put as stored gas. And similarly, we have a propulsion system called chemical propulsion system. Under that, we have different classifications. So that is where we were telling about the solid propulsion using solid kind of a fuel, liquid propulsion using a liquid propellants, and then we have the hybrid, means both solid and liquid put together. And similarly, under the liquid propulsion, we have 2 categories. One is by pressure fed. A simple meaning is that the propellants are fed from the tank to the engine by pressurization. And there is another type called pump fed, where the propellants are fed to the engine by pumping method, by taking the propellants from the tank and building up a high pressure, because you need a higher flow rate and a higher thrust. So you need a higher pressure. We go for a pump fed. Moving on to the right, we have the advanced systems. We talk about the electric propulsion. There again, the different versions are there. It is called electric thermal propulsion, electromagnetic propulsions are there, electrostatic propulsion devices are there. We will see it later. And similarly, we have an advanced system, advanced propulsion called the nuclear propulsion. There again, nuclear thermal propulsion is there, nuclear electric propulsions are there. And then we have further propellantless propulsion. That is where the propellants are not required using the solar power or within the, the sun pressures, the photons. Using that, we can sail in the orbit. And we have a laser propulsion. So these things, some of these, we will see it in the later. Now, we will address each one of them in very quick session, like stored gas propulsion. As the name indicates, the gas is stored in a gas bottle that you see the yellow colored, the gas bottle at the top. It is called propellant tank. This gas can be helium, this gas can be nitrogen or whatever it is. And that is at a high pressure. And then we have a series of certain valves and the regulators, so that once you open these valves, the regulators will regulate it to a needed pressure. It could be 18 kc or it could be 20 kc, depending upon what is the thrust that you want. And that is a simple, very simple mechanism, like, you fill a balloon and you just open the balloon, the gas comes out, the balloon moves forward, something like that. So here again, the gas is stored in the gas bottle and then it is fed through the thruster by the operation of various valves and through the operation of regulators. So these are all mainly used for control systems in satellites when your demand for the thrust level are very less, of the order of 1 Newton, 10 Newton kind of a thing. So these are all mainly for that. Now when we look at the solid propulsion, these propulsion motors, they are all ranging from small motors to big motors, which are all finds its application in the launcher or in the launch vehicle application. As you see here, the cross-section of that is a very simple system. and very robust also, very reliable, because the number of elements are less. So you see there is a yellow portion which is called the combustion space. There is a gray portion which is actually the propellant. So, and then there is a motor case. So and you are seeing a red colored badge which is on the left side. This is the igniter. So for igniting a solid propellant, you need an igniter. So igniter is ignited by means of electrical command. So you give a command from the onboard, and using the battery, you supply the electrical supply to the cube, a small electrical wire, which will raise the temperature, and that will ignite this very small solid propellant inside the igniter. So once the igniter catches, immediately it ignites the main propellant, the gray color, the full length of the chamber, it gets ignited. And once the total propellant gets ignited in a controlled way, combustion will happen, and then it will exhaust to the right side. That is called the nozzle. It is basically a convergent divergent. It is called a D-level nozzle. Who are studying the space, they may understand what is the D-level nozzle, which is again a conversion divergent nozzle, where the high pressure is getting converted into high velocities of the order of, in terms of Mach number, it will be very high. When we are having a Mach number of 1 at the throat, which is called the sonic velocities, and they said you will have a very high Mach number equivalent to the velocities of something like 2000 meters per second or even much higher. When we talk about solid propulsion, it must be 2000 or 3000 meters. But when we talk about advanced propulsion systems, it can be as high as 10,000 meters per second. Or you can always convert it into a Mach number, because Mach number, one Mach number is something like 340 meters per second, the velocity of sound. So always you can convert that. So here you get a huge power, a huge thrust, and which is what is required for a launch vehicle when you take off from the earth to overcome the gravity. So naturally, all the launch vehicles will use these kinds of boosters, like a solid boosters. Moving further, we have another propulsion called liquid. Here, the main advantage is, compared to solid, this liquid, you have a better controllability. And you are also having a higher performance in terms of efficiency. And in the rocketry, when we call it as efficiency, we term it as in the terms of specific impulse, especially it is called ISP. That is the amount of thrust that you get when you fire 1 kg per second of a propellant. So this is a parameter which otherwise, in nominal automobiles, we call it as horsepower. So here the horsepowers are in millions. So we don't normally talk about the performance in horsepower, because it's in lakhs and millions. So, but then we derive a parameter called ISP. So the liquid propulsion system have got a better ISP, or a better specific impulse. That's why we say it's a higher performance. Better controllability, because always you can shut off or switch on by just switching on the valves, or closing the valves, or opening the valves is always possible. And another advantage is basically, you can always flight test this, because in the ground you can test it and use it for the flight. Whereas solid propulsion, it is a one-time operation device. Whatever that solid propellant is stored, once it is ignited, the full propellant will be going out. So there you can't test it. So here in the liquid, we have a restart capability. You can switch off and switch on. All these things are there. So that's why liquid propulsion is gaining advantage over solid propulsion. But then solid propulsion has got its own advantage of creating a high power, high thrust. Very short time, you can create a high thrust. And as a boosters, always people use solid propulsion. Even in our Indian launch vehicles also, all of the launch vehicles, whatever we have seen, PSLV, GSLV, LVM3, or in SSLV, you are seeing a solid boosters giving the initial needed thrust to overcome the gravity and things like that. Of course, any propulsion has got its own disadvantages. In terms of liquid propulsion, it has got a number of parts, therefore it is more complex. And the reliability also, maybe the reliability always you can build up by going for a number of testing. But it always has more preparation. You need to fill the propellant at the launch pad, being a liquid like that. So these are all the things with respect to the liquid propulsion. And it's a simple sketch which is shown here, that you have a rocket, you have 2 tanks. Always for a combustion, you need 3 things. One is the oxidizer, other one is the fuel, and the third one is the temperature. These 3 things form the 3 vertex of a triangle. That is called the safety triangle, or it's a fire triangle. So here we have fuel, here we have an oxidizer. So where from the temperature comes? It can come either from an igniter, or when the propellants mix, that is called hypercooling. That means certain propellants are the fuel and oxidizer. When they mix, they create a huge exothermic reaction. And this reaction, it produces huge amount of energy, thermal energy, which ignites the propellant. These are called hypergolic. But then there are certain propellants which are not hypergolic. For those propellants, we need an igniter, like a cryogenic propellant. So we have a different categories called monopropellant, bipropellant, and bipropellant also we have a pump fed and pressure fed, which we will see it. So here, Basically, as you see in the picture, both the propellants will flow through valves to the engine where it mixes, and when it gets ignited, high pressures are created, and these high pressures are getting converted into high velocities in the nozzle, what is seen on the right side, extreme right, like a convergent divergent, where the exhaust is going at a very high velocities. So basically the thrust you are getting because of the Newton's third law, every action there is an equivalent opposite reaction. So here the mass as well as the exit velocity, it is called m dot into velocity, exit velocity. That is the momentum which is actually pushing the vehicle forward. So you get a reaction back which is acting as a thrust. That is how any propulsion will work on. Now you see the monopropellant. As the name indicates, it is a single propellant. There is only one propellant, which is actually simple. It is very simple. You just store it in a tank, you open the valves, and then it goes to the thruster. Then what happens is this monopropellant, it is admitted through a catalyst, and the catalyst bed, it is maintained at a certain temperature, maybe to 300 degrees centigrade, where the propellant, something like a hydrazine, it is a propellant, or even a hydrogen peroxide is another propellant. These gets dissociated or decomposed, creating high temperature and pressure, and that is admitted to the nozzle to get the required thrust. So these are all, it is used for control purposes in the satellites, and then in all our IIRS class of satellites, these kinds of monopropulsion systems are employed. Now let us see what are the various, the propellant combinations in a bipropellant. As the name suggests, there are two propellants, fuel and oxidizer. These are the propellants. Of course, there are various kinds are there. These are all only examples. You see the storable propellant. The meaning is it can be stored in the earth conditions. No separate environment is required to store the propellant in the earth-like environment, like in an ambient pressure and ambient temperature. So the propellants oxidizer like nitrogen tetroxide. Fuel is put in red color everywhere. The red colors are fuel, and there's an unsymmetrical dimethyl hydrazine. This is one combination, or you are having another combination, nitrogen tetroxide with monomethyl hydrazine. These are all storable. You need not have to have a different kinds of environment to store it in the tank cages. Whereas when you come to cryogenic propellants, these are all, as the name suggests, it is cryogenics. Means it is below minus 150 degrees centigrade. You can imagine the water becomes ice at 0 degrees centigrade. We are talking about 150 degrees centigrade below that. So minus 150 below that, anything is cryogenic. So the oxygen and the hydrogen, or even the nitrogen for that matter, all these are in gases, and below these temperatures, it will become liquid. Liquid hydrogen will become liquid only when you go to 20 Kelvin or even minus 253 degree centigrade. And similarly, liquid oxygen is also, the gaseous oxygen becomes liquid at 90 Kelvin, minus 183 degrees centigrade. So such kind of low temperatures we are dealing is called cryogenic. Similarly, we have a semi-cryogenic where one propellant is storable, other propellant is cryogen. Here the cryogen is liquid oxygen, which is again 90 Kelvin, and kerosene is a room temperature, maybe 300 Kelvin you can store kerosene. But then it is a high quality kerosene, it is not the kerosene we use in a house. It is a superior kerosene, or something like an aviation turbine fuel, or we call it as an ISRO-zine. ISRO kerosene is called ISRO-zine, something like that. And similarly, already we dealt with monopropellant. This could be hydrazine, hydrogen peroxide. So these are all the various kinds of the propellants that we employ. Now let us look at, yes, this particular thing also, this we have already seen, the rocket where the tanks are put. On the right side, there is a picture showing the nozzle as well as the fuel and oxidizer tanks. And once you open the valves, it gets. And then here, only one point I would like to tell you. Whenever we deal with the liquid propellants, fuel and oxidizer, they are stored in liquid form in two different tanks. And therefore, the ratio at which you are admitting the oxidizer and the fuel to the engine is very, very important. We call it as a mixer ratio. And then the mixer ratio is nothing but it is a ratio of oxidizer to the fuel. That is what is put in the equation in the bottom. Otherwise, it is conventional things, and then cryogenic propellants always need an igniter, whereas storable, hypergolic, we defined earlier, hypergolic are the one where when fuel and oxidizer mixes, exothermic reaction is generated, high amount of heat is generated, and that ignites the propellant. That is where it's called hypergolic, whereas cryo is actually you need an igniter. So moving further, you can see again the pressure fed and the pump fed here. The pressure fed, as it is shown in the left side, you can see two tanks, simply the propellants are filled, and there is a space where you fill the gases. It is called allayed space, which is not filled with propellant. And in this allayed space, we pressurize either with nitrogen or helium. It simply pushes the propellant. Like, you keep water tank in our house at the over tank, you simply open the tap, the water flows to the pipe, something like that. Here, these propellants are stored in a tank. It is pressurized by means of a pressurization bottle, which is shown as a spherical bottle in the top. And once you open the valves in the below about the nozzle, the propellant simply flows, and there it meets and combustion takes place. You get a combustion, you get a thrust. It's called the pressure point. On the right side, whenever you want higher flow rate, higher thrust, you go for a pump fed because you need a higher pressure. One way is you pressurize the tank, but then when you pressurize the tank, you have to build a big thickness for the tank material, and that will lead to very high inert mass. So we always do this calculation of thrust weight, and then which is better, whether pressure fed or pump fed. Then we find pressure fed, pump fed is better when we go for certain, higher thrust kind of a thing. Where we use all the pumps, you see below the propellant tank there are pumps. These pumps will take the propellant from the tank and then it will pump it to the engine or to the the thrust chamber. And then, but then for driving the pump, you need a turbine. So we use a gas turbine. So this gas turbine also has to be driven by gas, hot gas. So how do you produce the gas? So the same propellant which is coming from the tank to the nozzle, whatever that is going outside the pumps, especially we call it downstream of the pump, a small tapping is taken. You can see there is a small tapping is taken both in the fuel line and in the oxidizer line, and then it is given to a gas generator where the gas is produced, and that gas runs to the turbine. Maybe the arrow mark or the mouse can show that. So that goes to the turbine, and then the turbine is run, and these gases will be dumped on board. It will go out. So some energy is used for driving the turbine, and this turbine will drive all the pumps, and the pumps will take propellant from the tank and pump it to the engine. That is how the high flow rates are getting produced and high thrust is being produced. This is a simple operating principle of a pump-fed system. Now you see, even in a pump-fed system, there are different thermodynamic cycles. How the combustion cycles are taking place. We have a gas generator cycle, we have a stage combustion cycle, we have an expander cycle. There are different kinds of cycles are there, depending upon the maturity of the design, depending upon the expertise in the design. So we adopt certain design cycles. Here you can see the gas generator cycle. This is what we have explained in the previous slide, where a portion of the propellant will be taken from the pump downstream, that will be admitted to the gas generator. Gas generator, the combustion will take place, that hot gas will go to the turbine will be run, and the gas will come out like an exhaust. And once the turbine is run, this turbine will be driving all the three pumps. Maybe if you want different speeds, we put a gearbox there. For the oxidizer, if you want a different speed, we turn the gear according to the gear ratio, the speed will be changed. So this is called the gas generator cycle. Here, one point to be noted is, after running the turbine, the gas, which is again contain the energy, it is simply dumped on board. So here you're not getting a full efficiency there. Now compared to the right side, there's a closed cycle. Other one is an open cycle because the gas is going out after the gas generator. Now you see on the right side, here again the principles are a small difference is there. You can see, you can trace the oxidizer, which is a blue line. From the pump outlet it comes, and then there is a tapping there. A small flow will go to the pre-burner, or the pre-burner is otherwise it is a gas generator. Similarly, you can also trace the fuel line, which is red line. From the pump it comes, entire thing is going through the chamber. You can see it is cooling the chamber, and when it's getting cooled, the propellant will get heated up, and that it will, the temperature is going up. More pressures are created, that is admitted. The entire propellant goes to the pre-burner, and a small amount of oxidizer is coming, there it will mix, and then you are getting, that high temperature, that will drive the turbine, and then the turbine, again, the whole gases will come back to the main chamber. So that means here I am not losing the gases, I am taking it back to the thrust chamber, and I am getting a good efficiency. So this is called a stable combustion cycle. You can move further. So now hydrogen, cryogenics, already we have defined, always the cryogen has got a very high, the power, the thermal power is available. There is a good advantage over there. All these things are the only disadvantage is this is very lightweight, and therefore you need a bigger tank volume to accommodate this much huge quantity of hydrogen. Otherwise, enthalpy wise, it is having a very enthalpy. Always people go for cryo because of higher enthalpy, but you cannot use it as a booster stage because huge tanks are required to store the propellants. So it has got an advantage and disadvantage. So according to the requirement, either we will use it in the booster stage or we will use it in the upper stage of the rockets. Yeah. Now this is the same thing. I think this we can skip. Already we have told this. These are all the various, the cryo engines. USA, ESA, China, Russians, and India. You can see all these engines are used in the upper stage of the respective launchers. And you can see the right bottom, we have two Indian engines, which is called CUS. There is a cryo upper stage, and similarly it's called C20, where the cryogenic engine with a 20-ton thrust level. So this thrust you can see 73 kilonewton as well as 200 kilonewton. It is comparable with the other USA or China or the Russian launchers wherever they use the upper stage. So similar engines, we have totally indigenized. The CUS is fully indigenized, and the C20 is an end-to-end indigenized engine. So India can be proud of that. The total cryogenic technology we are having to build even bigger cryogenic engines for the future launch vehicles. Now, semi-cryo, as the name suggests, one part is H-storable, other part is cryogen, that is a liquid oxygen, and of course kerosene. So naturally, when we go for semi-cryogen, one important parameter to be noted is the density impulse. Density multiplied by the specific impulse. This plays a very important role for selecting any propulsion when we design the full launcher. So normally the semi-cryogenic engine or the semi-cryogenic propulsion we use for a booster stage. So here I have two advantages. One is it has got a good density, second, so that your container size can be less. Other thing, it has got a moderately high ISP compared to the H-storable. Already we have seen it is about 330 to 350 seconds. So that way the density multiplied with specific impulse, it gives a good number. Probably in one table I will show you, maybe the next, maybe we will see that. You can go to the next where we can see the table here. In the table you can see the last row. It is called the density into ISP. It's called the density impulse. You can see semi-cryo something like 3000 plus, whereas H-storable is only 2800 and cryogenic is about 1500. So for all the booster stages, we use semi-cryogen. Semi-cryogen is also one technology which India now is almost done. We had certain engine tests. Now we are going to full steam. Maybe in a year, the semi-cryogenic stage also will come. So our plan is the bottommost line you can read, the GSLV Mark III, we are planning to convert the core stage. Earlier we have seen it's a H-storable stage, which we are planning to convert into semi-cryogenic stage so that we can increase the payload capability by about 700 kg. So that is where the booster stage we will use. But if you use for the upper stage, that is what is shown in the above line. In the current LVM3, the upper stage is cryo. If you are replacing with the semi-cryo, there could be a payload loss because there the performance matters in the upper stage. So that's why there is a payload loss. But normally when you go for the booster, always there is a payload gain. Now let us see the hybrid motors. As the name suggests, hybrid motors are the one which use both fuel and oxidizer, where fuel is the solid and the oxidizer is liquid. Here the advantage is you can always start and stop. Unlike solid, if it is a fully solid, once you start, the total motor will burn till the total propellant is exhausted. Whereas a solid plus liquid means once I switch off the oxidizer, the combustion can be stopped. So it has got that advantage. It has got a moderately high the specific impulse also. Here the oxidizer what we use is either it can be a liquid oxygen or it could be a hydrogen peroxide or nitrous oxide. So it has got a shutdown and the restart capability is always there. Depending upon the mission, we select these kinds of things. Anyway, currently in none of our launch vehicles, we are using hybrid, but already this particular engine has been developed and it has been test proven in our ground test facilities. Yeah. So this table I think we have already dealt with, where I wanted to only tell about the ISP. Solid we are getting around, last column we can see around 290 maximum. H-storable we get up to 315. Semi-cryogenics up to 350, whereas the cryogen we can get even up to 440 to 460. So this is the kind of the efficiency that we get depending upon the different kinds of propulsion. So it is all left to the designer and his expertise available to select what kind of propulsion he is expert in, and then accordingly the launcher can be designed. Yeah. Yes, these three launch vehicles also we have seen. Maybe we can see further. And these are all the liquid stages. Like, the extreme left, we can see the PSLV. It is using two liquid stages, which is again using the H-storable, like, nitrogen tetroxide and hydrazine. And similarly in the middle, GSLV Mark II, we are seeing there again the second stage and the cryo stage. We are seeing that. And the right side, we have the LVM3. Why this slide is put is just note that launch vehicle Mark III, we have two major booster stages are there. One is the L110. Always the number represents the propellant loading. 100 tons of propellant. Similarly, C25 is there with 25 tons of cryogenic propellant. Just remember these two stages, L110 and C25. I'll be referring this in my next slide. In my next slide, you can see on the left side, there is an LVM3. You can see the bottom, the middle colored one, you can see that is the L110 stage today. This particular stage, we are going to replace with a semi-cryogenic stage. You can see SC120. 120 refers to 120 tons of semi-cryogenic, which consists of liquid oxygen and nitrocene. So once that L110 stage is replaced with semi-cryogenic, we get a good payload advantage. Added to that, the top stage, the cryogenic stage, which is currently C-25. 25 tons only we are using the propellants, which we are having a plan to upgrade it to C-32 with 32 tons propellant loading, and added to that, even the engine thrust also, we are planning to upgrade it from the current 20 ton to 22 ton. So by doing both these changes, you can see the bottom, the payload capability is enhanced by more than 1 ton, from 4 ton to 5 ton or even 5.1 ton capability. This anyway we are going to demonstrate in a matter of another 1 year. And on the right side, we are going to have a new gen launch vehicle. It's called next generation launch vehicle, which is really required for us when you are talking about going to moon and all, in the future. This is very important, which the designs are already in the final stage and the realization actions are also taken. You can see there is a core stage which is called the LM450. It is a LOX methane. This again, make a point, make a note that it is using LOX and methane. Again, both are like, cryo. LOX and methane, which is again low cost because the methane is again cheaper. And then it is about 450 tons of propellants are used in the core stage. And we have a second stage with LM120 and we have an upper stage with C-32. This particular launcher is gigantic. It is something like 5 to 5.4 meter in diameter. And then height is about 90 meter tall, which has got a huge capability of taking 20 to 30 ton to the low Earth orbit, or even to up to 10 to 12 ton to the geotransfer orbit. So this is a huge launcher in a matter of few years. This launcher also will come, which is actually a dream for us for taking humans to moon in the future, when our vision is already there to put our man on moon by 2040. So for that, this launcher also will be coming into picture. You can see the kind of engines on the right side where we are clustering all the engines together for the core stage, and for the second stage, LM120, we use 2 of them for our second stage, and upper stage, of course, it's a cryo. So moving further, now again, this is already we have dealt with, maybe we can move further. Now let us talk something about our advances. Green propulsion. Green propulsion, basically, all these propellants we talked about, that's storable, they are all highly toxic. So when we talk about they are not eco-friendly. So when we talk about that, we need to think of which kind of propulsion can give me a better eco-friendly propellant, environmental friendly. When we think about that, there are propellants like, hydroxyl ammonium nitride or even ADN, kind of ammonium dinitride, like of propellants are there, which is otherwise called green propulsion. That means once these decomposes, you get, the exhaust will be totally eco-friendly, something like steam or carbon dioxide or carbon like that only is there. So these kinds of green propellants are also, we are doing R&D, as well as even now, many thrusters have been designed and tested. Maybe in the future, we will be using these kinds of propulsion system for our satellite application. In fact, the greenness of the propellants are measured by means of lethal dose and lethal concentration. That way, that is called LD50 as well as LC50 kind of a thing, where, when we expose these kinds of propellants, 50% of the population should not get affected. So when we tell that quantity of the propellant required, when number is higher, means it is more greener. For extraordinary or chemical propulsion, the number will be on the lower side. That is how the rating of the greenness is done. So these are all some of the green propellants like, HAN, ADN, or even a bipropellant green propellant is there, something like hydrogen peroxide and ethanol, or hydrogen peroxide and isoleucine. So these are all already we have tested, and maybe soon this may find applications in our satellite. Now, again, it is only to show you that this green propulsion we have used even in the human space mission by Americans in the first, the Mercury, which has carried Alan Shepard as well as John Glenn, the astronauts from the America. They have all traveled in Mercury, and that uses these kinds of green propulsion for controlling the modules in orbit. Similarly, the Soyuz, which is there in the bottom, which is a very, very versatile space capsule designed during the 1950s, and even today, so many flights have taken place, which is also using monopropellant for their, the on-orbit control, or even during the descent control. Mainly, they are using for the descent control. Yeah. Now let us see the advance again, the nuclear propulsion. Here, nuclear thermal is there. As the name suggests, basically, it is very simple. You have a nuclear energy, nuclear fuel, something like uranium, U-235, or even U-233, kind of a uranium. Nuclear systems are there, which, you can always use that nuclear fission or a fusion to generate huge quantity of heat, and that heat will be, it will be used for raising the temperatures or converting the low pressure to high pressure of the propellants like hydrogen and all. And this high pressure, the gases will be pushed through a nozzle so that you get a thrust. So that is what it is called the nuclear thermal propulsion. So here, basically, huge quantity of heat is generated because of the nuclear fission and fusion. So you get a huge thermal power. That way, you get a higher ISP. So here, when you get a nuclear thermal propulsion, maybe NTP, like what is shown in the bottom side, The red color shows the hydrogen, what you assume, the nuclear reactor, and there is a hydrogen tank on the right side, blue color. Hydrogen is admitted to the nuclear reactor, where the huge amount of heat is generated because of the nuclear fission of the fuel, and that heat is used for pressurizing or increase the temperature and pressure of hydrogen, which is ejected through the nozzle by a thrust. So you get a higher thrust, and a huge amount of energy is there. So good specific impulse you get, and in a short time you can reach the destination. So it has got that kind of an advantage. So like moving further, you can see the various engines which have been designed by Americans and Japanese. So the Kiwi is again Project Rover. It is like Kiwi is like, flightless bird. Like that, this has already been tested. It has never flown. This is called Project Rover during the 1959 and 60. And similarly, the nuclear energy vehicle for the launch vehicle, especially for the rocket vehicle assembly. So this propulsion called the Narva, which is again, it has not taken off, but then this testing also have taken place during the 1970s, and this also by the Americans. And on the right side, we have the Russian. This also uses liquid hydrogen, and then there is a nuclear reactor which is used for generating the thermal power to convert this liquid hydrogen into gaseous hydrogen to a very high pressure and pushing it through the nozzle. These are the kind of thrust that you are getting. For the Russians, you are finding around 35 tons or 355 kilonewton, and the American engines are also giving you almost 24 to 25 tons of propellant. So these are all the kinds of the nuclear thermal propulsion engines, and we can see the latest ones are the Draco as well as the Copernicus, again by the American companies. They are again working on the nuclear propulsion, and even you might have heard about the Prometheus, the project which has been taken up, and today it is all shelved. That is also planned to work by nuclear thermal propulsion or nuclear electric propulsion. So the principles are same. Using the nuclear fission, generate the heat. That heat is used for heating the propellant, hydrogen, and then the propellant is getting converted into gas to a high pressure, high temperature, pump it through the nozzle, get the thrust. In the nuclear electric propulsion, what we use is these kinds of same thermal energy is produced, and this thermal energy is converted into electrical energy. Probably a gas will be heated, that gas will be running the turbine will run the generator, and then electricity will be produced. This electricity is used for static, the electric propulsion devices. So that is called the NEP, or the nuclear electric propulsion. So this is the other kind, which I have already explained. So here again, the bottom one you can see, Project Prometheus. So this is anyway, it is shelled, but then this gives very high ISP. This particular electric propulsion, something like 3,000 to 4,000 seconds also it can give. So here again, the work already, we are also doing some work towards that. Maybe it all will come in due course of time. This is again forming part of advanced propulsion. Now coming to the electric propulsion, there are three categories: electric thermal, electric static, electromagnetic. The three things are now basically, you can see the electrothermal, basically as I said, using the electrical energy. You may ask me, where from the electric energy? It is from the battery or from the solar panel of the satellite. Use the electric energy to to heat the propellants and then eject it through the nozzle. So it's an electrothermal. And then electrostatic is nothing. That is, you have a high power electric energy is available. That is used for ionizing the gas. Here the gases we use something like noble gases like xenon or argon or krypton. These gases will be ionized by putting a high potential across the anode and the cathode. And these ionized gases are attracted towards the nozzle by means of the cathode, where the electrons are there which will attract the positive ions at a very high speed and ejected out through the nozzle, giving a very high ISP, something like 3,000 to 4,000 seconds. In the electromagnetic, again, a magnetic energy as well as the electric fields are created to ionize and then to make it plasma and then eject the matter through the nozzle. So these are all the various principles which are used for electrothermal or electrostatic and electromagnetic. One point to be noted is that electrothermal, you may get a slightly higher thrust, but then ISP compared to electrostatic is low. Electrostatic, you get a very high ISP, but the problem is you get a low thrust because the ions are getting ejected. It will be in millinewton. Electromagnetic is also of the same kind. You get a higher ISP or higher efficiency, but the thrust level will be on the low. So all these things forms part of future or even current satellite propulsion. People are already using. US has already used, Europeans have used, and we are also planning to use electrostatic propulsion in our upcoming satellite called the Technology Development Satellite, which we are going to fly in the next mission of PSLV in the first half of this year. This static propulsion also we are using it. And this is only the basic, the building blocks. For electric propulsion, you need three important things. One, you need the power control. That is called the power system, which will have the required electrical power. And then there has to be an electronic control system. Second thing is a feed system. You need a gas. It should be stored in a bottle and that to be admitted to the thruster by providing certain regulators and wires. So that is called the feed system. And the third one, of course, the thruster, where the electric thrusters are needed, where it consists of anode and cathode, where it is getting ionized and then is pushed out through the nozzle. So this is the building block of the electric propulsion system. And electrothermal, already we have seen, we are putting coils around the chamber to heat the propellant and push it through the nozzle. It's a simple thing. Vasimir, that is a variable specific impulse magnetoplasma thruster. It is again a form of electrothermal. It is also a form of electromagnetic the RF kind of a thing. Basically, the RF is used. Radio frequency is used for heating the propellant. By varying the radio frequency, the heat energy can be varied, the thrust can be varied. That is why it's called variable specific impulse. ISP can be varied. So it is again a form of electrothermal. And moving further, we see the electrostatic. Here again, as I already mentioned, you have an all-effect thruster, which creates a magnetic field to trap the electrons once the gases are ionized. And then these ionized gases are attracted towards the cathode by means of an electric potential between the anode and cathode. And very high velocities it attracted, and that gets ejected through the nozzle at even 10,000 meters per second, creating very high ISP. So this gives a very high ISP but low thrust. Moving further, this we can see the xenon, argon. It is only the graph showing what is the kind of ionization potential that is needed to ionize the gases. You can see the xenon, which is shown in a yellow, the dotted circle. That gives the least ionization potential. Whereas krypton and argon, they are all noble gases. It requires slightly more ionization potential. So generally we use xenon, but then xenon is costlier. We can also use argon, but argon has got a higher potential. So it can be used either way. It all depends upon what is the cost that is, you can put it like that. And now electromagnetic, I think this we have already explained. It is a magnetic field is created to trap the electrons, and then you have a high electric potential acting between anode and cathode to attract the ions, and then that is how the propulsion also you are getting. So the final thing is basically the propellantless propulsion. This is a very interesting thing called a solar sail. Once the satellite is injected, doesn't require any propellants at all. It will simply, a big surface area will be there. Even it can be as high as 1,500 meters square, a 50 meter by 30 meter kind of a sail, a thin membrane, as shown in the picture on the right side. You can see a thin membrane will be there, and that will be pushed by means of a solar pressure or the photons that will be acting upon it by changing the momentum. It creates the force, and that force pushes the satellite also forward. So this is a kind of propulsion device which does not require any propellants, but then it is available free in space using the solar pressures. But then this we can use it only within the solar system. But beyond the certain planets, the solar power source will be less. So for deep space or interstellar space or beyond the solar system, this may not be viable. But within the solar system for interplanetary mission, these kinds of solar sail is always advantageous, which is already like a mission called IIRS, that is interplanetary kite. It's accelerated by radiation of the sun. So using the radiation of the sun, acceleration is got, and like a kite, it will be flying between the planets. So IIRS mission has successfully flown. Similarly, they have the night sails. 2 missions were there in 2015 and 19 of Planetary Society of US. They are also there. So this is a very feasible option, which is called a propellantless propulsion. Something like a sailboat, what you do in a water, like wind pressures it flows, something like that. So I think with this, I conclude. And thank you very much. I think in a short time, we have gone through the chemical propulsion. We have seen the various propulsion, solid, liquid, bipropellant, various kinds of cycles. Also, we have seen the advanced propulsion, including the electrothermal, electrostatic, electrodynamic, magnetic, as well as the nuclear thermal, nuclear electric, and also the propellantless propulsion and so on. So I think with this, I conclude. Thank you very much. Now, over to the audience for any questions.